Question 9 is a moments question. We can tell it's a moments question when they start giving you lengths on your diagrams. That's a really big giveaway. Notice we've got another alpha, and if I scroll down a little bit, we've got that tan alpha is 3/4 again. So in the same way that when tan alpha was 3/4 in the other question, we knew that sine alpha was going to be 3/5 and cos alpha is 4/5. We can do the same thing here. So we've got a plank A to B here resting horizontally against a rough vertical wall. If the wall is vertical and rough, that means there is friction between the wall and the plank, and that friction will be up in this direction, because it must be, if it was going to slip, it would slip downwards, so the friction must be acting upwards to stop it from slipping down. What else have we got? We've got we've got a mass, the plank is of mass m, and if we read a bit further down, it's modelled as a uniform rod, which means we can add, I've got the diagram again down here, we can add halfway along a weight of mg newtons, where that distance is A. We also have, if I scroll back up, that little box P, which has a mass of 3m. So that's going to have a weight of 3 mg. We also have a rope here that's connecting C to B, that's connected to the wall and is being kind of pulled kind of this way to keep the plank in place, which means there's tension in that rope there acting towards the wall. I think that's, I've lost my friction. Now, we don't know what that friction value is, so if we're going to hope to work out T, we're going to need to take moments about A, so that we can ignore the friction. So if we tell the examiner what we're doing, let's take moments about A. And we're looking to be able to write something down about the tension. It says show the tension in the rope is this. So if we look at clockwise moments, then we've got this mg times A, and we've got the 3 mg from the block, 3 mg times x, needs to equal the anti-clockwise moments, and the only anti-clockwise moment we've got is this one from the tension. Now the tension is going to be T times the perpendicular distance from A. The perpendicular distance from A is going to be this distance here. And if we work out what that distance is, that is going to be 2A cos alpha. No, it's not. It's going to be 2A sine alpha, because this is the opposite. Now we've already said that sine alpha is 3/5. So we've got 3 times 2, so 6t or 6at over 5. We can simplify this too. So 2 times 3/5 is 6/5 times the a times the t. On this side, we've noticed we've got an m and a g, which we can factor out. The last couple of steps are dead straightforward. We're going to need to times by the 5, and divide by the 6a to give us our t. And that's what we had. Okay, part B then says that the magnitude of the horizontal component of the force exerted on the plank at A by the wall. So that is a force acting inwards like this towards the plank is 2 mg. Find x in terms of A. So what we have, remember we found the tension acting from B to C in part A, that's this. Now the only other horizontal force that we have is the horizontal component of T, which will be T cos alpha. So because it's not moving, because it's in equilibrium, 2 mg must equal T cos alpha. So we can write down that 2 mg is equal to T cos alpha. T we worked out in part 1 was that 5 mg A plus 3x over 6a, and cos alpha is 4/5. We worked that out too. So there's a few things that we can cancel. We can get rid of the mg's, and that's going to give us 10 a plus 3x over 6a is equal to 2. Oh, no, it's not. Totally made that up. We've got 2 is equal to, these 5's are going to cancel as well, and we've got a 4 over 6 here, which we can change to a 2 over 3, a plus 3x over a. The 2's cancel, these 2's here, so we've got 1 equals a plus 3x over 3a. If I bring the 3a up, I subtract an a, we get 2a equals 3x, and they wanted x in terms of a. So x is equal to 2/3 of a. Okay, part C then says that the force exerted on the plank by at A by the wall actually acts. So we've got some force acting at A, makes an angle beta with the horizontal. So we've got some sort of force here, which is it's the frictional force, but I drew it earlier going up. Is that they've actually said it's coming at an angle here, where that angle is beta. We already know the vertical component of the horizontal component of that force. They told us, we worked that out in part B, or they told us that it was 2 mg. So we already can say straight away that this F cos beta is equal to 2 mg. Now it will have a vertical component as well. So it's got a vertical component coming up here that will be F sine beta. Notice we've got a sine beta and a cos beta, and thereafter a tan beta. So at some point we're going to want to divide this one by this one. That will make the F's cancel, and whatever it's equal to on the right hand side, if we divide it, that will give us the value of tan beta. So that's the main aim, but we've got a few steps to do before then. Now we're going to want to, we wrote this down because it's true, but also because if you remember from part B, we were resolving the horizontal forces. We used the tension, the vertical component, the horizontal, component of the tension, and said that that was T cos alpha. There's a horizontal component of the tension as well, which will be T sine alpha. Don't forget about the weights as well. We had a weight of mg for the plank, and we had a weight of 3 mg for the block. So all the forces are on there now, and I've accounted for all of the angled forces. I've turned into vertical and horizontal components. So again, just like with all the other questions that we've done on this paper, we can now resolve vertically and horizontally. We've already done it horizontally. We're going to do it vertically now as well. But before we do, I'm going to simplify this formula that we've got for tension, because we worked out in part B that the tension is 2a over 3, and that x is 2a over 3, and that's useful because we can simplify what we've got in here. So if I do that, if x is 2/3 of a, I've got 3 x's here, so that's going to be 2a. So we can say that T is equal to 5 mg times a plus 2a over 6a. That's 3a over 6a, so that's going to cancel to just 2. So T can now be simplified to 5 mg over 2. So that's really useful because that's going to simplify all this stuff down. So we already know that F cos beta is equal to 2 mg. But if we look at the vertical components now, we can say that F sine beta plus T, which is 5 mg over 2, times sine alpha, which is 3/5, is going to equal the downwards forces, which is going to total 4 mg. If we simplify that, the 5's will cancel, and we'll have the F sine beta is equal to 4 mg minus 3 mg over 2. 4 minus 3 over 2 is going to be 5 over 2. So 5 mg over 2. So we've now got that F sine beta is equal to 5 mg over 2, and F cos beta is equal to 2 mg. If we divide sine this by this, that will give us tan beta is equal to 5 mg over 2 divided by 2 mg. The mg's cancel, and we're left with 5 over 2 times 2, so 5 over 4. So tan beta is 5 over 4. Okay, finally it says that the rope will break if the tension exceeds 5 mg. Now we've shown in part A that the tension can be written as this. So this needs to stay less than or equal to 5 mg if the rope isn't to break. So P is the point where the little box is. So if you can imagine, this can slide up and down here, but if it gets in certain positions, the tension will become too much. So as it moves this way, there's going to be more tension on the rope as it gets closer and closer to B, and at some point it's going to snap if the tension exceeds 5 mg. So we can use this relationship to work out the valid or the acceptable positions of P in terms of X. So if we can cancel out the 5 mg's and say that 3x plus a needs to be less than or equal to 6a. And if I subtract an a, then x has to be less than or equal to 5a over 3. So that's where the box is okay to be it can slide up and down here, but it has to stop, can't go further than 5/3 of A. If it does, the rope will break. So in order to answer the question fully, it says answer carefully, we need to say that X or P must be less than or equal to 5A over 3 for the rope not to break.